Welcome back to the Solutions Manual. In this video, we will solve the problem 3-14 from R.C. Hibbeler Mechanics of Materials 8 edition. According to this problem, the rigid pipe is supported by a pin at A and an 836 steel guy wire BD. If the wire has a diameter of 0.25 inch, we have to determine how much it stretches when a load of 600 lb acts on the pipe. Now to solve this problem, first of all we have to draw the free body diagram. Point A is pin connected, so we have a vertical support reaction and the horizontal support reaction. We have a tensile force due to this wire BD. Let's label them. So this right here is AX. This is AY. Let's call this FDB. Now we have to resolve this FDB force into its components. So we have a vertical component and the horizontal component. Let's call this angle theta. The vertical component is FDB sin theta and the horizontal component is FDB cos theta. For angle theta, we can consider this triangle ABB. For theta, consider triangle ABD. So we can use the ratio of tan theta. So tan theta is equals to opposite, which is 4, over adjacent, which is 3. So theta comes out to be 53.13 degrees. Now we can apply our equations of equilibrium to find the force in the wire PB. My first equation is summation of moments at point A equals to 0. I am considering counterclockwise direction as positive. Since the line of action of AX and AY is passing through the point A, so these two forces do not have any momentum with respect to the point A. So AX and AY will not produce any moment about point A. The vertical component of FDB force is trying to rotate the pipe in counterclockwise direction about point A, so the moment produced by FDB sin theta will be taken as positive. So we have FDB sin theta and theta is 53.13 degrees. And the moment arm is this 3 foot distance. The line of action of FDB cos theta, which is the horizontal component of FDB force, is also passing through the point A. So FDB cos theta does not have any momentum with respect to the point A. So FDB cos theta will not produce any moment about point A. This external load P is trying to rotate the rigid pipe in clockwise direction about the point A. So the moment produced by the force P will be taken as negative. So negative P, and the moment arm is the length of this pipe, which is 3 feet plus 3 feet. So 6 feet in total, equals to 0. So upon simplification, we have sin 53.13 is 0.8 into 3 into FDB minus P is 600 lb. So 600 into 6 equals to 0. So from here, FDB comes out to be 1500 lbs. Now we have to find the average normal stress in the wire BD for sigma BD. So the average normal stress in the wire BD is equals to force FBD divided by the cross-sectional area of the wire BD. So FBD is 1500 lbs divided by the cross-sectional area of the wire BD, which is the area of the circle. So pi by 4, diameter is square. Diameter is 0.25 inch, 0.25 square. The average normal stress in the wire BD comes out to be 30,557.75 psi, which is less than yield stress of 836 steel guy, which is 36,000 psi. So we are still in an elastic region. So Hooke's law is applicable. So Hooke's law is applicable. For average normal strain, if we use the Hooke's law, we would have average normal stress BD is equals to the Young's modulus into the average normal strain BD. If we rearrange this equation, we would have average normal strain is equals to average normal stress over the Young's modulus. The Young's modulus of 836 steel is 29,000 KSI. Average normal strain is equals to sigma BD, which is 30,557.75 divided by the Young's modulus, which is 29,000 KSI. And since we have to convert it into the PSI, so we have to multiply it by 1000, so exponent 3. So average normal strain comes out to be 1.054 exponent negative 3 inch per inch. So this is our average normal strain. Now we have to determine how much is the stretch in the wire BD when the load of 600 lbs is applied. For stretch BD, we can relate the average normal strain and the stretch BD by this formula, which is average normal strain BD is equals to stretch BD over the unstretched length of the wire BD. So for unstretched length, we can again consider this triangle A, B and D. For unstretched length LBD, LBD is basically the hypotenuse of the triangle ABD. So we can use the Pythagoras theorem. So LBD is equals to square root of 3 square plus 4 square. So LBD comes out to be 5 feet. But since we are working in the pounds per square inch, so we have to convert this 5 feet into inches. So we have to multiply it by 12 because in 1 foot we have 12 inches. So LBD comes out to be 60 inch. So the stretch BD is equals to average normal strain BD into the unstretched length LBD. So we have 1.054 exponent negative 3 into 60. The stretch BD comes out to be 0.0632 inch. So this is our final answer. So this is it for this problem. I hope you would find this video helpful. If you do, please make sure to subscribe to this channel and turn on the bell icon for the daily updates. And if you have any questions or any doubts in the free body diagram or in the properties of the material, then feel free to ask in the comment section and I will try to answer them as soon as possible. Thank you.